Now, throughout the year, you're going to see things referenced as postulates or maybe axioms. We're going to talk about theorems later. But the first thing we're really going to come across are things called postulates. Okay? And a postulate is really an accepted kind of mathematical truth, and there's no need to prove it's true. Now, we will talk about things that we will need to prove that are true, and those are theorems. And you guys might remember the Pythagorean theorem. And that's something we'll get into later this chapter. So when you see postulates, think of them as just like truth nuggets, like a truth that we don't really have to prove. So the first postulate we're going to talk about is related to how many points it takes to make one unique line. And so I'm going to start off with just one single point here, point H. Now, someone might say, I could draw a line, and I know this is going to be a line because I want to put arrow caps on the end, and hey, look, one point made a unique line here, and I know I kind of messed up down here, but just ignore that for now. Here, I'll kind of make it. I know it's a different color. Some people's OCD is going off the radar here, but it's okay. All right. Now, notice I said a unique line. Well, I could draw a different line that also goes through point H, right? And so it's seeming like it's going to take more than just one point to make one unique line. So I'm going to need to call some help from South America. South America? Oh, look, point P. Cool. Now, if I had 2 points and I wanted to make a line, notice I would make that line. They would have to go through both points. I know it's not going through both points yet. Just give me a second here. There we go. And then let me just readjust this point. There we go. All right. So now, if I had this point, or not a point, this line, it's going through both points. Now, could I draw another line that is different than this one that goes through those same 2 points? And some people might be like, oh yeah, I can totally can do that. Look, this comes up here, and then it's going to come down here and go through point B. There's a second line. But if you remember earlier when we defined a line, we said lines are going to be always straight. They aren't going to be curved. They're not going to be bent. Always straight. So could you draw a straight line through these 2 points that's different from this one line that I've already drawn? And the answer is no. So how many points does it take to make only one unique line? Well, here in your notes, it's going to take 2 points to make a unique line. Now our next postulate says if 2 lines intersect, so notice we've got a line here and we got another line here, and they're intersecting, then their intersection is a what exactly? So if I had line PC and line NK, and they're just going to run into each other, what do you think we would define their intersection as? And we would define it as a point, right? But notice there is no point actually drawn at this intersection, right? Like notice point N, it's got a point right next to it. Point P's got a point C's got a point K's got a point, but this R right here, there is no actual little point at that intersection. So if you ever see 2 lines cross, you're going to have to see a letter there, or you're going to have to define it, but there should be a letter defined there. So when 2 lines intersect, they will intersect at a point. And so here's point R, the point of intersection, where they meet or come together. All right, so let's practice with some intersections here. So just a quick example. Line PS. Okay, so well, here's P, here's S. So we must be talking about this line as line PS. And let me grab a different color here. Line QU. Well, here's Q, here's U. So remember, lines are infinite length. So I'm just going to stretch this thing out, and it's really this whole thing. So where do those 2 lines intersect at? Well, they come together and meet at point R. Now remember, you don't just write R, because what are you, a pirate? You're not going to name that R. You have to call it by its proper geometrical name, which would be point R. And that would be the answer I'm looking for. So if I just said name the intersection of these 2 lines, and you just wrote down R, you've got part of the answer there, but officially you don't have the full correct answer. You have to put that word point in front of the R. Now, what if we tried one without an actual picture? And you might go, whoa, 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 that seems impossible. So if I had line WR and line RB, where would they intersect at? Well, if you wanted to, you could draw a picture of what this scenario would look like. Pretend we just draw a line. So let me draw this red line here. And let's make this line WR. So somewhere on this line is point W, and somewhere on this line is point R. So hey, look, there's line WR. So now I need a second line, line RB. Well, where would line RB be located at? Well, we know that it would have to go through point R, but where, what kind of angle would it be at with respect to line WR? It really doesn't matter. Okay, so let's imagine this is going to be line RB. Now, point B has to be somewhere on this line, so let's just say I put it further up here. Okay, where do those two lines come together? Well, at point R they come together. So some people might look at this and go, well, so let me hypothesize here. If you gave me the name of two lines, I think that whatever letter they may have in common, that would be the point where they would intersect together, those two lines. And I would say that's a good hypothesis. Now, can you always do that to be able to identify the point? And I would say no, because look back at our last example here. I gave you line PS and line QU, and there is no common letter here. Now, that was because I picked P and S, and there was really a third point on this line, right? Point R, and I gave you line QU, and there was a third point on that line that I didn't use, which was R. So if you do notice a common letter between two lines, you are guaranteed that that common letter that those two lines share will be a point of intersection. So here, I guess we need to give this a proper answer here. Point R, once again. All right, collinear points. This was that we really defined what non-collinear meant earlier, but collinear points, here's your official definition, is that they're just points on the same line. Points on the same line. And again, that co means together, like to cooperate. You're going to operate together. So together on a line. And what's together on a line? Points are together on a line. Now, coplanar points, so instead of points being on the same line, it's going to be points that are going to be on the same plane. Okay, so collinear, coplanar, going to be on the same line or on the same plane. Now, as we start to wrap up this first video here, imagine I've got an ice cube, all right? And on that ice cube, I've got a lot of different points here. I've got points A, B, C, D, E, F, G, and H. And the first question I have for you is, how many planes are in this ice cube? And so some people might be quick to rush here and say, well, there's 6 planes, right? There's the bottom plane. There's the top plane. There's the left plane. There's the right plane. And there's the front plane, and there's a back plane. And I would say that's a good start. There are 6 planes certainly there. The top, bottom, left, right, front, and back. But technically, this thing has infinitely many planes. And you might start to question, well, what other... There's only 6 sides to this thing. And it's true, there are 6 sides, but just imagine what would happen if you connected together points E, H, C, and B. What if you had a plane that kind of diagonally sliced through this ice cube? Right? That would be a plane. That would work. And so you could do the same thing for really any of the corners, right? You could take A and D with F and G up here, and then there, and that's kind of harder to see, but there would be a plane that would slice it diagonally that way. And really, there are other points that we haven't defined besides A through H, but like I could come along here and say, well, let's call this point I, let's call this point back here J, let's call this K, let's call this L, right? And so here could be another plane that kind of slices it horizontally. Not necessarily in the middle, but there's another plane that could exist there. So the actual answer of how many planes are in this ice cube, technically there's infinitely many. But how many are we really going to talk about? Probably the main six, right? The left, right, top, bottom, and front and back. So the next example, where do planes DAB and FGC intersect? So now we're going to talk about the intersection of planes. And we haven't officially talked about where they intersect, but we're going to kind of discover that together. So plane DAB, let me grab a different color here. D, there's A, and where's B? There's B. Now, a lot of people initially will look at plane DAB and they just connect them together like this, and they go, hey, that's a triangle. And if I look in this triangle, man, there's no other points in that plane, right? But remember, to name a plane, we needed at least three non-collinear points. Is there another point that's in the same plane as D, A, and B? And if you notice, point C over here is still in the same plane, right? We can kind of think of this all as the bottom plane. Now, so DAB, we could also identify as DABC, all right? So that we just left out a letter. So sometimes you'll see three. Maybe they'll put a fourth one in there. We don't know. And then where's the other plane at? Let's get a different color here. FGC. So here's F, here's G, here's C. Again, I only gave 3 points here. Is there a fourth point that would really make a better defined looking plane? And B would really, right? Because then that would give us this entire right side of this ice cube, this entire right plane. Well, where do these two planes come together? Where does the floor, imagine this ice cube as a room, where does the floor meet up with the right side of the wall? And really, it's connecting down here from B to C. And it's all of these other points in between, right? That we're not defining what these points are, but there are technically infinitely many points from B to C. And so how would we name this intersection? Well, remember, planes are infinite. So it doesn't just start at B and end at C, or start at C and end at B. It really goes on and on and on forever past C and past B. So how do we name this specific thing? Well, we would call it line BC, or you could call it line CB backwards. Either way is acceptable. So it seems like when two planes come together and they intersect, they're going to intersect at a line. So the next postulate. If two planes intersect, then their intersection is a line. So again, notice I've got this kind of purple plane intersecting with this, I don't know, greenish, I don't know what color you'd really call that, teal plane maybe. But if we notice where they intersect, I see point S and I see point T. But keep in mind, technically, these planes are infinite in length and width. So it's not just point S and T, but it's all the points that are on this line. But we would properly call this line ST, would be the intersection of those two planes. And then our last postulate that we're going to talk about in this first video, we're not done with the video after this, but this is our last postulate. It says through any blank non-collinear points. Remember, non-collinear meant that they don't all line up. There is exactly one plane. And so I mentioned why non-collinear. And so I have this picture here that we'll talk about. But notice I have 3 points already drawn out here, right? And if those 3 points are collinear, notice I've got them all connected up there. Now, let me go back here for a second. There we go. Notice I've got all these points kind of lined up. But if they were collinear, then technically I could have a yellow plane hit all 3 of those points. I could have this green plane that's kind of slicing at them diagonally. It could hit all 3 of those points. This pink or purplish looking plane, it could hit all 3 of those points. But notice this postulate is asking about exactly one plane. So if I had 3 collinear points, how many planes could go through those 3 collinear points? Really infinitely many, right? Like I drew 3 here, a yellow, pink, and a green plane, but there could be another plane that goes in between the yellow and the green plane, There could be a plane that goes in between the green and the pink planes. And then you could just keep going on and on forever in that motion. So we need three, but they need to be non-collinear points. And you can have exactly one plane. So let me just show you a quick example here. Let me just draw three non-collinear points. And so we could say, hey, your computer screen or your phone screen contains all three of those points, right? Contains all three of these non-collinear points. So we have exactly one plane there. Your screen is one plane. Could you take a piece of paper and touch all three of those points, and it wouldn't coincide, it wouldn't be really, on top of your screen. And just like with planes, or just like with lines, sorry, planes have to be flat. We can't make them curvy or wavy. Planes have to be absolutely flat, just like lines have to be absolutely straight. So your computer screen is the one and exactly one plane that contains those 3 points. There, you couldn't take a piece of paper and touch all three of those points without it being really the same as your screen. Now, the last three examples, and this is something I will commonly do in my videos, is usually at the end, maybe scattered throughout the video, I'm going to leave some problems for you guys to try. All right, so I have three problems here that I want you to try. Example 6, 7, and 8. And so these will be problems that we can discuss the next day in class. All right, so try those three problems out. And again, if you get stumped on them, if you get stuck, if you don't feel confident in your answer, it's okay. These aren't worth a grade. These are just for you to try to apply what you've just learned from the video. So good luck with those, and we'll talk about them the next time in class.